So our final section is if we are integrating over a volume. So for example, I think the one we're going to think about here is, suppose you've got a volume, a three-dimensional shape. This is kind of something, I don't know, like a rugby ball or something like that. And say you want to find the mass of it. Now, to find the mass of it might be to find the volume unless the density is non-uniform, as we are imagining in these examples. So maybe like this, whatever this three-dimensional object is, maybe it's denser at the bottom than the top. How would you find the mass of it? Well, what you do is you chop it up into loads of little pieces, small pieces, little volumes, and you would find the mass of that little volume, and then you'd add up all those little masses. And adding up, and of course if you chop this fine enough, you're talking about infinitely many, infinitely small things, so that is integration. But the integration now is over a volume. Okay, so these are called triple integrals when you're adding up over a volume. So we're just going to have one example here, which is finding the mass, and kind of similar to before, if rho is the density per unit volume, then multiplying the density by the little bit of volume gives you a little bit of mass. Add up all the little bits of mass, you get the mass of the volume. We are only going to add up over boxes and cylinders. Okay, so let's see this example here. So a box is given by, now this notation means that the x coordinates go between 0 and 2. The y coordinates go between 0 and 3, and the z coordinates go between 0 and 7. Now I have a picture on the next page, but we'll just show you what I mean here. So x goes between 0 and 2. So that'd be the x direction. Y goes between 0 and 3. And therefore you have this. So that's the base of the box, and then the z would be the height. Up to 4, so you'd have now I'm not a great artist, so I want the same height going up, or I could come across here a little bit. Something like that anyway, that's supposed to be it. Okay, so we're going to find the mass of this box, but the density is equal to 2x y squared z cubed, and we're assuming SI units and its mass, so the answer will be kilograms. So what we're going to do is, so this is the x direction. Now we have some more picture on the next page, but I think the picture I just drew is possibly more useful. So this is the x direction, this is the y direction, and this is the z direction. So what we're going to do is we're going to fix y and z to be constant, and we are going to, so that means that we've got a fixed height and a fixed distance along here. So we're going to find, now it's saying a horizontal strip, but you could also think about it as a little rod going across. So I think you could call it a strip, you could call it a rod. So it's supposed to be going from one side of the box to the other side of the box. Note that it's a fixed distance along the y, it's a fixed z. What's changing is the z coordinate. So hopefully you can visualize this thing. Rod is probably a little bit confusing because it's like a square rod, because we're using these Cartesian coordinates. So let's find the mass of this square rod, or let's call it horizontal strip. I don't know what we could call it really. So let's go. So the mass of this strip, and the main thing to notice is that only x is changing. The y is fixed, the z is fixed. So this is going to be add up. Now this point is x equal to 0. This point is x equal to 2. Add up from x equal to 0, from x equal to 0 to x equal to 2, the density, which is 2xy squared z cubed, by the volume. Now, if it's a box, if you look, that means you're using these Cartesian coordinates. So a little box, a little dv is a little bit of x, a little bit of y, a little bit of z. Oh, I'm so crap at drawing, sorry. That was stupid. Let me try again. Now this is supposed to be kind of magnified because the boxes are really, really small. This is like dx, dy, dz. And so the volume, so I've written down the density, the volume is dx, dy, dz. Okay, now along this horizontal strip, only x is changing, so we've loads of constants here. So 2 is a constant, y squared is a constant, z cubed is a constant, dy and dz. So like if you look at this thing, I called it, it's probably more like a little beam, and so dz would be kind of the height of it, and the width of it would be dy, they're constant. So this is kind of a rectangular cross section going across cross section area dy dz. The whole way across is constant, so I can pull them out as constants. And what am I left with? The integral from 0 to 2 of x dx, which is not a difficult integral because we know that x is like x to the power of 1. So to integrate this thing, we do, now all this stuff is stuck here. We could get a bit lazy and kind of do dot dot, but let's do it. 2y squared z cubed dy dz. Integral, or the antiderivative of x to the 1 is x squared over 2. I'm going from 0 to 2. So we do top limit minus bottom limit. I get 2y squared z cubed dy dz. And then I'll go, okay, well, I'll go a little faster. So I got 2 cubed, 2 squared over 2 minus 0 squared over 2. 2 squared over 2 is 4 over 2 is 2, so the 2 multiply, this is 2 by 2 gives me, I get that the mass of this strip is 4y squared z cubed dy dz. Now because dy and dz are very, very small, the cross-sectional area of this strip is very, very small, and so the mass of this is essentially 0. But we're going to add up all these strips as we go from the y equal to 0 strip all the way to y equal to 3. We're going to add up the mass of all these strips, and that will give us the mass of, I suppose you call it the plate or the sheet at a fixed z. So we add up this mass from here, which is y equal to 0, add up to y equal to 3, we get the mass of a plate. This is what we'll do in the next page. So this is the box there. The volume is that. Okay, so the mass of a plate, the plate we've kind of drawn on the previous page, add up from y equal to 0 to y equal to 3, the mass of a strip at y, at a fixed y, but y is changing now, and a constant height. So the mass of a strip is 4y squared z cubed dy dz. Now across this plate, what's constant is the height, and dz is kind of the width of this plate. That's also a constant. So we can take out anything that isn't y as a constant. So 4 is a constant, z cubed is a constant, dz is a constant, and we're adding up from 0 to 3 y squared dy. Now this is a relatively easy integral because it's just antiderivative of y squared is y cubed over 3. And now you want to do your top limit minus bottom limit. So we get 4z cubed dz, and then substitute in top limit, that's 3 cubed minus 0 cubed. 3 cubed over 3, so I'm substituting in the y equal to 3 into this, minus substituting bottom limit, 0 cubed over 3. 3 cubed over 3 is 3 squared is 9, 0 cubed is 0, so this is 9 by 4, giving us 36 z squared dz. And that is the mass of a plate at a fixed z. Now what we have to do is add up the mass of all the plates, or the sheets, from z equals 0 up to z equal to 4, and that will give you the mass of the box. So you find the mass of the box by chopping it up into little pieces. First you find the mass of a strip, then the mass of a plate, and then add up the mass of all the plates, you get the mass of the box. So m, which is what we're looking for, the mass of the box, add up the mass of the plates from z equal to 0 up to z equal to 4. And the mass of a plate is 36z squared dz. Now you can take out the 36 as a constant here, but you can just fix it as a constant in the antiderivative instead. Fix the 36, and it was z cubed, wasn't it? Sorry, my bad. Z cubed. So the antiderivative of z cubed is z to the 4 over 4. And go from 0 to 3, and it's now 36 divided by 4 is 9. So it'll be 9, substitute top limit, 3 to the 4, minus 9, substitute bottom limit, 0 to the 4. Remember, you can pause me at any time. And I think that's 9 by 81, which is probably 810 minus 81, but we'll just do it on this. I get 729. And it said SI units, so if everything is in SI units, then this would be the SI units of mass, which is kilograms. So that's the first one, finding the mass of a box given the density. Not too bad.